You must have a T block for the hardware implementation where you will have all the power rail in case of the breadboard, but in case of the Vero boards and PCB board, you need the T block for the OT, for the ground, and for the common power. Then, what do you say? So here we have this is called T, common ground power bank. So all of these grounds should be connected or should be drawn from here. So I mean that, for instance, that you can take a jumper and connect with this one. So we have connected the common ground. We have connected the power supply for the AND gate. So when you connect the power between pin number 14 and pin number 7, all the logic gates built-in integrated circuits have power. Okay? So these are the common pins for four logic gates, or 6 logic gates, or 3 logic gates, or even 1 logic gate. You should not claim that all the ICs have 4 gates. No, you should not claim. It's your responsibility to go and check the physical appearance of the other integrated circuit. So let us say that, or let us make decision. We say, okay, let us use the CD and the gate. And then we need again another input T, called T, put B. Okay? Okay? Limb is drawn. Why? You know the reason. What the color of LED that we'll be using there? A? Red. These concepts are very important when we'll be designing RF transmitter and RF receiver, after I taught you the concepts of encoder and decoder. Okay? So what the resistance of this resistor, massa? What the resistance of this resistor, massa? Massa is not in the class. Physically she's there, but 240. So resistance of this resistor, it's 240 ohm. Say ohm. Because you may just remember 240, but you forgot ohm. And 240 is meaningless. Class, are we together? Are we together? Remember that. Remember that. This ground, it's just a wire from here. This ground is just a wire from here. This ground is just a wire from here. As this ground is just a wire from there. Remember we said that in any electronic circuits, we need to have common OT, ground. So simply, just see for the matter of representation, this is a common ground. So physically, you need jumpers. Are we together, class? Yes. Is it clear? Don't forget to label or to name. This is figure what? A? Figure 3. Then, what its name? So once you have that schematic circuit diagram, what you just need, just electronics components and build it and test it. How are you, everybody who have connected to this wonderful workshop? I would like to take this opportunity to welcome you into this interesting moment of learning about how we can design electronics digital communication circuits or electronics digital circuit. If it's the first time to meet me, I'm very happy to have you. This is Olenjolai. I am from Tanzania. I thank God by His own grace, I am a local and also a national teacher in teaching just the 5 fields, but one of the fields is actually about electronics engineering and telecommunication engineering. So by God's grace that today I will be standing the positions of teaching about electronics engineering and telecommunication engineering. However, that the modules is in the sections of telecommunication engineering, but actually that we need some concepts in electronics engineering. I would like to take this opportunity to welcome you to join us and concentrate and pay attention. This will be a closely practical session or closely practical workshop, because the information that we are going to discuss, these are more than theoretical concepts. We have discussed about the theories of the half adder in previous workshop, which is workshop number 2. So in this workshop number 3, we actually continue where we ended in the previous workshop, but also we'll be paying attention how you can implement, what are the requirements, what should you think as electronics or telecommunication engineer in order to make sure that you grasp the concepts and you have a successful implementation. But remember that in this workshop, we are going to have schematic diagrams, we are going to have diagrams, we are also going to have numbers, because teaching engineering without numbers is actually less effective compared to in case that you have numbers. But again, in this workshop, we are going to have table of results, and also we'll be discussing about the measuring instruments that you are using in digital experiments. So I think that is the clue, or that is the overview of today's workshop. You are strongly powerful. Make sure that you have all the requirements, and let us go to the class. But I have a number of students who have joined me in this wonderful moments. And these students are pursuing Bachelor in Electronics and Telecommunication Engineering at Dar es Salaam Institute of Technology. This is one of the leading institutions in our beautiful country that's called Tanzania. So let me respect them and let us join together. How are you, students? How are you, Electronics and Telecommunication Engineering students? Are you ready for workshop 3? Well, so let us go. Stay connected, stay focused from the beginning to the end. So let us discuss, or let us do a quick review of what we have discussed in previous workshop. In workshop number 2, the title of the workshop is actual. I have built a foundation about how can you design digital electronics circuits or system. How can you design digital electronic circuits? Then I told you that, or I taught you, or how can you construct? How can you design? How can you construct? I taught you 6 steps. 50 steps that you have to follow. And we'll be following these 6 steps in every design that we'll be discussing. So 6 steps that you have to use on designing digital electronics circuit. The first step, tell me the first step, you have to identify number of inputs and number of outputs. Simply this we call I/O. So I stands for input, O stands for output. Robert. We are just starting the class, and then we are making stories with Toba. So you have to identify the number 40, the number of input output peripherals or inputs and outputs in your design. The second step is what? Tell me, students. Okay, so you have to create a truth table. So you will see, why did we teach truth table since a level or ordinary diploma in engineering? Why did we teach you the truth table? Because you need it when you want to design a digital electronic circuit. And then the next step is what? Pardon? So they use the Boolean what? Expression. So all about Boolean expressions, if you don't know them, so if you did not understand, I'm teaching another module that's called digital electronics to the second year bachelor, or to the second year bachelor engineering students who are pursuing mechanical in our institution. And after this class, I will have that class. So you are warmly welcome. So they use the Boolean expressions. When we talk about the Booleans, this is the NASA or Boolean algebra. This is the NASA, or this is the one of the branch of algebra. In real life or in real situation, algebra, we have two branches of algebra. The first one, linear algebra that you've been learning. The second one, Boolean algebra, which we introduce students for the first time when you reach to the college or to the university level, or third, or we call it tertiary education. So this is actually a very powerful branch of electronics, and there's a lot of things to know about Boolean expressions. Okay, then the next step, we say that you have to simplify. You have to simplify the Boolean expressions that you have reduced in the first step. And once you simplify, for this case, you'll be using Boolean algebra laws. Then the next step, which is the fifth step, if the Boolean algebra law fail, then we say that use other method. Use other method. Use other method of what? Of simplify. I think that I said use schema, but in digital electronics you have four methods of simplifying a Boolean expression. So Boolean algebra laws, that the first method, and the second one is schema. But also you have some other two. I don't know if you are familiar, but if you're not familiar, you can consult your teacher of fundamental digital electronics, because those are the fundamental skills that you should have. So you should not limit. So even they came up, if came up fails to simplify, you have to go to the steady method. And if also the third method fail, you have to go to the fourth method. When all the four methods fail to simplify Boolean expression, then you can conclude that Boolean expressions cannot be simplified. Class, are we together? Okay. Then the last step, we say that now implement. Implement your implement your design. Then after that, we use we use the 7 steps to design. Okay, to design what? To design half adder. And then after using this method, we had a block diagrams of half adder, which actually had 5 blocks. The first one, we call it input binary unit. The second one is called DC power supply unit. The third one is called the half adder unit. And then the other one is called the sum. And the other block is called the carry. So in previous workshop, we say that whenever we open we discussed about how to open the block of half adder. Then we discussed also about Sally. Class, I told you that whenever I'm teaching, I'm using a lot of energy. My mind is here. I'm trying my level best to teach you in a very simple language. I ask all students to be serious. So we say that whenever that we open this block of input binary unit, then we have different input binary unit. One of them, we say it can be either digital sensor, or it can be a pull-up resistor network, or it can be a pull-down resistor network, or it can be toggle, or it can be what we call it bit generators. So you say that to simplify the concepts, we usually just use the pull-up resistor or pull-down resistor network actually that to demonstrate the two states of the digital signal. So lastly, we discussed, I introduced to you the concepts of the Boolean, of the OT, of the pull-up resistor network. And when I've introduced it to you, we discussed it. I don't know, in case that maybe you've missed it. What did you say? We say that pull-down resistor network, let me just repeat this quickly. Resistor network, we say it's actually consisting of three components. The first one, we say that the power source, and then we have what? The push button. The push button. This is push button. Push button. And then another, or the steady components, it's called the resistor. And then we say that we have two testing points, very important testing point. For this point, we will have a voltage across the push button, and also we'll have another testing point. However, that the very important testing point is this one. This can call to A, and this one can call to B. So this is we call it voltage across the resistor. So this is the C voltmeter. Then we connect it across resistor. So this is pull-down resistor network. And then I told you that you can, it means that why do we like to use this? First of all, we don't like to use them, or we like to use them because these are the ones, or we use pull-up resistor or pull-down resistor and pull-up resistor network in digital a lot. Are we together? Are we together? Yeah. So we drew these diagrams. It was figure number what? Figure 2 or figure what? Figure 3. So this is schematic circuit diagram of what? Of pull down resistor network. So when we discuss about pull down resistor network, it means we open the input binary unit, or we open the block of input binary unit. I asked some students before starting the class when we are behind the scene. Then some students, they told me that we did not open. We just opened one block of the OT half adder. So let me just clear that concept because it was the end of lecture 2. Maybe your attention was not in the class. Let me just remind and insist you. Having that network, we have already opened the second block. And then we just told you that to remember about or to recall about laws that we've been learning in physics. And the laws that we've been learning, so we say that you have to recall Ohm's law. However, that just I spoke directly, Ohm's law. And with Ohm's law, we say that VCC and ground, this representing the C power supply. So it just opens also the steady block. This represents the C power supply. So simply we say that according to Ohm's law, the supply voltage is equal to voltage across resistor plus voltage across push button. Isn't it? Okay. So the push button and resistor are connected in series. So you say that we'll have I times R plus OT voltage or times I times resistance of the push button. So remember that for the series connection, current is common. I told you. He said that, sir, you are doing unfair. So VCC is equal to I, resistor. So that is your Hannah Samandito who is serious, showing that now I'm serious, now I'm serious, now I'm serious, now I'm serious. So that the seriousness of who? Samandito, man from Geita. He traveled from Geita to Dar es Salaam, several kilometers to come to seek this knowledge. And then, what's going on? So current is constant. So make current the subject. We have VCC resistor plus resistor of the push button. Another one from Shinyanga or from Mwanza to Dar to seek what? knowledge. Okay. Hey, this is just the beginning of the class. And I have more than 100 minutes in this class. So this is one of the mathematical questions. So we are trying to link the practical information with the theoretical information that we had. Shane, come with your stuff. So then, theoretically, this is what we say that we are trying to find the formula for the calculated values or theoretical values. So theoretically, we say that the voltage across resistor will be equal to the current times resistor. This will be our second equation. Then we say that. So sit there. So this is the first step. So this is the second step. So the third step, we usually used to say that in physics, substitute equation 1 into equation 2. Once we do that substitution, we find that voltage across resistor is equal to what the current, VCC over resistor plus resistance of the push button multiplied by resistance. So, if that's the case, we say that, so this is our final mathematical equation. Well, if this is the case, we say that in most cases, for the pull-up resistor, we use 10 kilo ohm or 5 kilo ohm or 1 kilo ohm in most cases. 10 kilo ohms is commonly used. So if the resistance at this point is 10 kilo ohm, and because that we are going to supply the C power to the digital or to the electronics components, the digital electronics components such as logic gates, all the logic gates, they have operating power ranging from 4.5 volts up to 5.5 volts according to their data sheet. So the typical value for this case is just 5 volt. Okay? Okay? Yes. Are we together? Yes. Getronica? So for that case, you say that the theoretical calculated values of the voltage across resistor, it will be 5 volt. Then the resistance is 10 kilo ohm. So just 10 kilo ohm, change it into ohm, plus resistance of the push button. When the push button is not pressed, so we say that when the push button is not pressed, we'll have two values. I told you that we'll have two values for this case. So the first state, so this is the first state. So for the first state, we say that when the push button is not pressed, then what you say? For that case, you say that resistance across or resistance of the push button is infinity resistance. Why? Because it's open circuit. So whenever we have open point, so resistance is what? Infinity. It's large. That's why there's no flow of current from this point to this point. First of all, I said stop writing. First of all, if the push button is not pressed, there is no flow of current. Right? Why is there no flow of current? Because of infinite resistance of the push button. This is not a closed loop. This is open. Are we together? So it means that when the push button is not pressed, the resistance of the push button is infinity ohm. Limi, Johanna, go out. Put yourself well. Hurry up. Hurry up, hurry up, hurry up, hurry up. Hurry up. Go out. So we say that for that case, you say that voltage across resistor is equal to 5 volt over what? Resistance of the pull-up, resistance of the pull-down resistor, it's 10 kilo ohm, which you convert into 10,000 ohm, then divided by infinity. Are we together? Then multiply by what? Resistance, which is what? 10,000 ohm. So infinity plus 10,000. What do you get? Infinity plus 10,000. What do you get? I want to hear the entire class. Infinity plus 10,000. What do you get? Simply trillion, 1 trillion plus 100 shillings. What do you get? Huh? It's almost 1 trillion. Huh? Huh? You will say that 1 trillion is 100 Tanzania shillings. Okay? So if that the case, you say that voltage across resistor, this is equal to what? 5 volt, multiplied by 10,000 ohm, then divided by infinity ohm. So ohm and ohm cancel. Right? Eh? And then 5 volt times 10,000. What do you get? Eh? Pardon? 50,000, isn't it? Eh? Over what? Eh? Infinity. 50,000 over infinity. What do you get? 50,000 over infinity. You have 1 mango and you are dividing to all the 6 million Tanzanians people. So each Tanzania will get what? Huh? Imagine I just have 1 orange and then I want to divide to all of you. How many oranges are you going to get? 0. So what were you thinking about? This is simple. So for this case, you say that this is 0 watt, 0 watt volt. So this is one of the theoretical. Then we go for the 5th step. For the 5th step, we say that when the push button is pressed, then for that case, resistance of the push button will be 0 ohm. Why? A push button is just 2 wires which will be disconnected and interconnected. So all the wires have 0 resistance. It's actually not 0, but it's almost 0. So if this push button, that push button is pressed, so the network change from open loop into the closed loop. Right? Right? So then we are going to have what? Potential drop. So there's mean that we'll have all the voltage will be pulled down towards the ground. So if that the case, we recall our equation. This is equation 3. So recall third equation. Engineering is all about equation. Once we recall the third equation, say voltage across resistor is equal to what? VCC, it is 5 volt. Then of what? Now, so it will be what? Resistor plus resistance of the push button multiplied by resistance of the push button. Is it clear? Is it clear? How did I get this? It's simple. We say that if you want to calculate voltage across push button, then this one will be current times resistance of the push button. Then we say that voltage of the push button, substitute the equations of the current, which was equation 1. This is equal to VCC over resistance plus resistance of the push button times resistance of the push button. Are we together? Are we together? Eh? No. No. We didn't finish the first case when the push button is not pressed. So we are still in these conditions when the push button is not pressed. So we have calculated voltage across resistor. Let us calculate voltage across the push button when the push button is not pressed, right? So fifth step. So for that case, voltage across push button will be equal to what? So VCC over resistance plus resistance of the push button multiplied by what? Resistance of the push button. So VB is equal to what? Resistance of push button over resistance plus resistance of the push button times VCC. If the push button is not pressed, what the resistance of the push button? Infinity ohm. If the push button is not pressed, what is resistance? Is infinity ohm. Plus what? Resistance, which is 10,000. Multiplied by what? Multiplied by 5 volt. So for this case, you say that voltage across push button is equal to what? Is equal to infinity. You said infinity plus 10,000 is infinity. Multiplied by 5 volt. So voltage across the push button, when the push button is not pressed, infinity over infinity is 1, is equal to 5 volt. So when you do simulation, you have to prove these values. When you do the hardware implementation, you have to prove these values. Okay? Are we together? Are we together? Okay. So the sixth step, we say that when the pushy button is pressed, so when the push button is pressed, let us start with voltage across push button as we started for this case. The formula will still the same, but there is just a small change because it's potential divider. We have resistance plus resistance of the push button. But for this case, we say that multiply by what? Multiply by resistance. But when the resistance, when the push button is pressed, its resistance RB is equal to 0 what? Is equal to 0 what? Is equal to 0 what, class? Ohm. So voltage across push button is equal to what? So you have resistance, which is 10,000 over what? Over 10,000 plus 0. Ohm and ohm will cancel. Multiply by what? Multiply by VCC. So voltage across push button will be 10,000 divided by what? 10,000 times what? VCC. Then voltage across push button will be what? 10,000 over 10,000. 1 will be equal to what? VCC. VCC is what? 5 volt. Are we together? In previous workshop, I've just mentioned these values. We didn't compute. Then let us calculate voltage across resistor when the push button is pressed. So when the push button is pressed, we say that the voltage across resistor, it's VCC over what? R plus what? RB multiplied by what? RB. I made a mistake, Okay, so I made a mistake. So this is because you are calculating voltage across base, across push button. Yes, RB. Thank you very much. So this is RB. So here we are going to have 0 ohm. Isn't? Isn't? And this one is 0. 0 over 10,000. 0. We don't have infinity anymore because the push button is pressed D. We have discussed that state. We have moved it to another state. Then, for this case, we should have R, isn't it? Voltage across resistor is equal to what? What is VCC? 5 volt. This one, 10,000. This is simple because it's just the potential divider. RB, 0. times 40, 10,000. 10,000 plus 0? 10,000. 10,000 over 10,000? 10,000 over 10,000? 1. 1 times 5 volt? Yes. So for this case, we have 5 volt. That's all about calculating the values in case of pull down resistor network. Is it clear? Is it clear? So we can move to the next C. We can move the next C block. So the next C block, it's the block of sum. So the block of sum, this is the block that you have to open. So the block of sum, we have different actuators. Simply in this block, we might have some indicators. Also, at this block, we might find, we call it another logic circuit. Or sometimes, for this case, we might find that the block of sum is connected with the display. We can also find that this one is actually connected with some actuator, or it's actual that's interconnected with actuator. Also in this block, we might find that in some scenarios, the block of sum is actual represents or interconnected with another block, which we call it some indicators, another logic circuit, display, actuators, and then the other ones which was coming in my mind, display, actuators, some. Yes, I think that there's also some other actuators. But for this case, we'll be just using the sum indicator to know about the summations of two binary inputs that will be added by the half adder system. So what is that indicator? So this you say that sum indicator. So this will be indicating the state that you have in sum. So sum indicator. So in this sum indicator, simply we just have what? We just have we represent this one. So this is the bubble, and this one we say that come from the output of the sum, and then we need to have a current limiting resistor, and also we may use a light emitting diode to indicate the state of the sum given by half adder. So because we are going to use two indicators for this one, we can just call it this is resistor. Its resistance just for current limiting, you may use between 100 ohm and 330 ohm. So for our case, we may use resistance of 200 ohm. And then this one, we call it green LED. Then we have the schematic circuit diagrams after opening the block of 40 of sum. We just need the indicator, because that indicator, the goodness of the LED, stop writing, the goodness of light emitting diode, it just have two working states, whether to turn on or to turn off. So actually that's representing also digital signal. Are we together? But that is in case of learning purpose. We don't mean that we are using half adders to turn on and turn off LEDs. No. Why are you hiding yourself? Again, we have the fifth block, which is carry. The fifth block, which is carry. Hello, Jacqueline, what's going on there? All the students who are sitting here, except Benjamin, is always the one who is focusing. All the other students, and Daniel Fortunatus. But the rest, halfly they're in the class, halfly they're outside. And some of them are experts. And they like to sit there. Then let us open the block of carry. So for the carry also, we can have a carry indicator. Carry indicator. We can also have another logic circuit connected with a carry, another logic circuit. It can be either the same half adder or maybe a encoder or any sequential logic circuit. This carry might be also connected with display, and also this carry, blocks of carry, might be connected with actuator. When you say actuator, class A actuators. So when you say actuator, for instance, motor is an actuator, buzzer it's an actuator, lamp it's an actuator, because I know maybe you don't have these foundations, etc., etc., etc. So similarly for the actuator, at this point it means that it can be either motor, it can be either what, a buzzer, it can be a lamp, etc., 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 etc. Are we together? Are we together? Are we together? Okay, so to simplify the concept, for our case, we just use the carry indicator, where we are going to use the LED, which will be working in only in two states. Either to turn on when the summation of the two bits is particular value, or to turn off when the summations of the particular bits is other particularity value. Are we together? So for the carry indicator, we'll be having the output from the carry of the half adder, and then we'll need current limiting resistor, be having a light emitting diode, and this one will be using red LED. Who can call Limi, Johanna, and Abdullah? Please call them. So this is ground. Then you sit down. Sit down. Sit down. Then this one, the resistance we are going to use for this case is 240 ohm. And this is ready light emitting diode. So for that case, we have finished our journey of designing a half adder. Now we are going to the overall implementations of the entire half adder system. Before I move to that point, if you have a question, ask me. Because what I'm going to draw, possibly have never thought about. Is there a question about what we discussed? If there's a question, please let me know. Class, I'm still giving you a chance to ask a question. If it's clear, let us move into the overall schematic circuit diagram that we'll be using to implement this system. Right quickly, I want to clean the entire blackboard. So now, the overall schematic diagram on paper and the simulation. overall schematic circuit diagram of half adder. So let us start with our DC power supply. So listen. So for this case, you say that we are going to use a battery. We are going to use a battery. In simulation, we have also a battery of 9 volt. 9 volt. No, default is 12 volt. In simulation, 12 volt. And then for that case, we have to use this is DC power supply unit. And then so you are going to use a voltage regulator. This is input, this is output, this is ground. This is LOM 7805. But in Proteus, it has been written as 7805. I say this operating, so drawing. Namfua. Then we expect it to have our power indicator. So this is the resistor. We may use 100 ohm. And this will be blue. Okay, so it will be 100 ohm. So we are going to use this we call it DC power indicator. LED or DC power indicator. So this is blue LED or blue LED. Okay, but remember that our output power we draw at this point, or we need this is a positive voltage. Then, because we say that this one will actually connect with what connectors. Do you remember? So connectors, we can use either 3 terminal, 3 T block, 3 terminals of T block, or 4 or 5 terminals of the T block. So for this point, we expect to have 5 volt. This is power bank. Okay? Okay? But in simulation, we don't need this. In simulation, we just need to take the wire. Then this is our 5 volt. This is our DC linear power supply. So this is in simulation. Yes. So yes, we need it. So this is our 5 volt linear power supply. Then we have to take on paper. And also in simulation. We need to have a pull down resistor network. For this case, we need a resistor of 40 of 10 kilo ohm. This is ground terminal. Then we say it separating. And also, because we are going, how many inputs do you have? How many inputs do you have, class, in alpha? How many binary inputs do you have? 2. So we need, so this will be our push button number 1. Okay, this is resistor 1. This is push button number 2. Then this is what? Resistor. This is ground. So here we have a pull down resistor of 10 kilo ohm. Are we together? Are we together? Are we together? Then we say that this will be a push button. Push button number 1. This is push button number 2. This is resistor 2. This is resistor 1. I said stop drawing, Shukuru, stop drawing. And then we say that now we are going to connect or to supply our input, first of all, to the sum. In sum of the half adder, we say we are going to use which type of the gate? Exclusive what? Exclusive OR gate. Silanga. Then also another input will be drawing from here. Okay? Okay? Then we have we have drawn the schematic circuit diagram for for sum. We said we are going to use a resistor, and what the resistance of that resistor that we said we are going to use in our design. Adamu, what the resistance of that resistor that you are going to use to represent in power indicator of sum. Pardon? 200 ohm. So resistance, it's 200 ohm. And this is light emitting diode. What Brighton, what the color of this LED that you're using in sum? Brighton is not there. Kankesha? Red. Are we using red in sum? Huh? Green. So Kankesha was not there. She was at Riverside. So this is green LED. Class, are we together? Huh? Then we say, how do we implement the carry? By using what? AND gate. Right? So we just take a wire and drop it from here. And then we have our first input. And then we have take a wire and take it here. And then have another input. So then this is our AND gate. Emmanuel Elias, you are drawing. I said stop drawing. Emmanuel Elias, what the resistance of the current limiting of the carry indicator? What the resistance? Dennis, what the resistance of this resistor according to our design? Adamu T. Adamu Juma. Tell us. Jacqueline, what the resistance of this resistor? Leave about Adamu and Elias. 240 ohm. You still have a great thickness of including unit in physical quantity. Say 240 ohm. 240 ohm. Urasa, tell us what the color of this LED that you are using in carry? Green. So green. It means Urasa is not in the class. Very good. Good try, but failure. Joanne, tell us the color. Red. So it's red. Ready LED. Are we together? So this is what you have to draw in simulation software and on paper. Figure 2, the overall schematic circuit diagram of half adder. Ask a question. Ask your question quickly. Ceramic capacitor. Wait, I just forgot. Thank you very much. I just forgot. Thank you very much. Here we have a ceramic capacitor. Of what? What the value of this ceramic capacitor? Sonia, what the values of that ceramic capacitor? 0.3 nanometer. Do you hear? Fatuma Makame, what the capacitance of that capacitor? 0.3 what? Mangoes? Micro. Very good. It's not 0.3, it's good try, it's 0.33 microfarad. Also here we have a ceramic capacitor to stabilize this power supply. What the resistance, what the capacitance of this capacitor, Digna? What the capacitance of that ceramic capacitor used there to stabilize the linear the power supply? The DC power supply. 0.33 what? Microfarad. Happiness, Lugano? What is capacitance? I don't need the story. I just need the number and unit. 0.1 microfarad. Very good. So the capacitance of this ceramic capacitor, it's 0.1 microfarad. 0.1 microfarad. So simply the battery plus voltage regulator unit plus the power indicator, those are the three blocks of DC power supply unit. I told you that we have DC power supply unit, we have linear power supply unit, we have switched mode power supply unit. In electronics fabrications, I told you about how you can design linear power supply unit. In this module, I've added a value how you can design DC power supply unit. DC power supply units, just you have three blocks. One block is just a battery because it's the source. The second block is just a voltage regulator unit. And the third block is power indicator unit. That's all. Are we together? But for you, you can put the transformer there and put the diodes. So now, let us draw overall schematic circuit diagram, logical diagram of half adder in hardware implementation. So because I want to draw with you, I think that it's better for you to finish this drawing because you are going to use that drawing to draw the second one. Hello? So this is the one point that you have to note. All the 7 logic gates remains that NOT gate, AND gate, OR gate, NAND gate, NAND gate, NOR gate, exclusive OR gate, and the exclusive NOR gate. All of them are built in integrated circuit. And for the case of the logic gates, we have 2 families. We have complementary, students, it's time to listen. We have complementary metal oxide semiconductor, which is called CMOS. And also we have transistor logic gates, which we call TTL in abbreviation. I won't go into details. In case you want the details of what I'm saying, you have to take my workshop that I used to teach in digital electronics. But simply that all of them are built in terms of integrated circuits. When you discuss for the TTL, it means that most of the integrated circuits of the logic gates, of the 7 logic gates, they have 14 pins. So for that case, stop writing. Let us start to draw our stop writing, stop drawing. Please take the pencil and pen of your neighbor. So we start with our DC power supply. So remember that in most cases, in case of the hardware implementation, we have batteries of 125 volt, we have batteries of 9 volt, we have batteries of 12 volt. But batteries of 12 volts are always heavier, just like a solar battery. A solar battery or a car battery, it is 12 volt. So the simplest one that you may use to implement, we are going to use a simple and portable battery of 9 volt. I will show you in case maybe we implement this one, you'll see it. And then we'll need to regulate this into 5 volt. And this one we say that we'll use to LM7805. For this case we have 40. So you have a ceramic capacitor of 0.33 microfarad. And then we have what? Ground. So this is ground, this is input, and here we have output. And at this point, we are going to have, we should have a T block or a male header or a female header, where that we are going to have our power bank, our DC power bank, to power different parts. So you can have just a T block of what? 5 terminals, 6 terminals. Yes, 8 terminals. 1, 2, 3, 4, 5, 6, 7, 8 terminals. And then this is resistor. What is the resistance of this resistor? 100 ohm. And then so we are going to have a power indicator. This is one of our communication system, half-adder, if you remember that we have mentioned them. What the color of this LED? Blue. Blue LED. Then we have what? Ground. But at this point, we also have another ceramic capacitor to stabilize 0.1. Why should we connect these capacitors? This is according to the data sheet or manufacturer's data sheet. Okay? And you have it. Then we have our power bank at this point. So listen, you may use either copper or a wire to draw power into the and connect it into one terminal of the push button. So this is push button number 1. Then for this case we have resistor. Resistor 40, 10 kilo ohm. For this case we have ground. Then we take another jumper or copper to draw power from the T block and connect it to the second pull down resistor network. In simulation you use the something you call the logic toggle to simulate. In hardware we don't have logic toggle. So this is a resistance of 40 of 10 kilo ohm. Okay. This is the physical appearance. of exclusive OR gate. It has 14 pins, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So here we have something we call it, or we have a marker, we call it notch. Class, say notch. Say notch. So by using this notch, we can count the pin numbers or the pins of any integrated circuit in anti-clockwise direction. So this is pin number 1, pin number 2, pin number 3, pin number 4, pin number 5, pin number 6, pin number 7. This is pin number 8, pin number 9, pin number 10, pin number 11, pin number 12, pin number 13, pin number 14. Then if we label this pin, the pin name of pin number 7, this is called the ground. Say ground. So this pin should be connected to the ground. And then pin number 14, this we call T VCC. VCC or VCC pin. So you have seen where should we supply power to the exclusive OR gate. In this exclusive OR gate, we call it its quadrupule. Quadrupules, it means that we call it quad exclusive OR gate. It means within it has just 4 exclusive OR gate. To implement our half adder, we just need 1. Right? Right? Yes. And how they have been connected to the pins? Well, this is how they have been connected. Pin number 1 and pin number 2, these are the input of the first exclusive OR gate. Pin number 3, this is the output of the first exclusive OR gate. Then we have what? Pin number 4 and pin number 5, these are the input of the second exclusive OR gate. Say second exclusive OR gate. Say second exclusive OR gate loudly. Second exclusive OR gate. Loud. Yeah, that's the sign. Then we have again the third exclusive OR gate, which is input pin number 9 and pin number 10. So this is the third exclusive OR gate. Okay? Okay? Shukuru, okay? Are you sure? Shukuru, are you sure? This is 8, 9, 10. 8, 9, 10, okay? 11. So I made a mistake here. This is 12. So pin number 12 and pin number 13, these are the input pins of exclusive OR gate number 4, or the fourth exclusive OR gate. That's the physical appearance of exclusive OR gate. Shadrach, I say it's not the time for drawing. It's a time to listen, reasoning, understanding. Then we'll be drawing. How many diagrams have you been drawing in your life or in electronics? So many. How many do you have in your mind? Few. So let us implement the exclusive OR gate part. It's simple once you have this diagram in hardware implementation. So pin number 1, this one is connected to the pull down resistor network number 1. This is what you used to call input A on paper and on simulation. Right? 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 Then this is our secondary input. Mikidadi, Mikidadi, Mikitadi, Mikidadi, and Pascal. So, once we add the 2, I say take your neighbor stuff. You are still drawing. Then we have supplied or introduced the 2 binary inputs to our exclusive OR gate. So then we need to have what we have to mean that what we have here is represented by this integrated circuit. Are we together? Are we together? I say what we have on paper, this is exclusive OR gate on paper and simulation. This is exclusive OR gate in hardware implementation. Are we together? Are we together? The IC number for that exclusive OR gate is 74 LOS 86 IC. 74, say 74 LO 8 LOS 86. Then we say that we need this SAMU indicator, right? SAMU indicator, you're using what? Green LED with a current limiting what? Resistor. Wonderful. So this is the point. What the LED do you have here? Seni? What the color of light emitting diode that you are using in this part? We have only one student that called the Seni in this class. Seni? Seni is not in the class. It's ready. Ready? LED. What the resistance? Resistance is what? 200 ohm. Pardon? Green. I know you are very expert in color of the LED. Thank you. So this is green, yeah? Okay, good. So we are done with the part of sum. So we just need to use only one exclusive OR gate. So we don't need to use this, we don't need to use this, we don't need to use this for this design. But for you, you'll say, in order for the circuit to work, let me use all the exclusive OR gates. Are we together? Okay. Then we have this part of 40 carry. Okay? So for carry, we have also another integrated circuit that is called the quad, or we call it quad duty and the gate. This is the notch. Say notch. Also the AND gate, the TTL AND gate that we are using in the in electronics, it has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. How do we number? All the students, show me the numbering. This is pin number 1. 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 And then where is number 2? This is number 2. This is 2. Then say it loudly. 7, then 8. 8. 8. Are we together? Then this pin is called the ground, the name of this pin. And this pin is called the VCC. Okay. Okay, let us come back. I forgot the names of other pins. Look on the blackboard. The name of the other pin, this one, we call it pin number 1A. And this is, no, 1A, yes. 1A, this is 1B. And this is pin number, or this is called the 1Y. This is 2A. This is called the 2B. This is called the 2Y. This is 3, 3A, 3B, 3Y. Then here we have 4A, 4B, 4Y. 4Y. Those are the names. We have pin numbers, we have pin names. Say pin number. Say pin number. Say loudly, pin number. Pin names. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is pin number. And each pin has its own name. Pin name is 1A. For this case, pin name is 1A. So 1A, 1B, 1Y, 2A, 2B, 2Y. Then for this one we call it 3A, 3B, 3Y. Where did they get this information? Ask your neighbor. Where did our teacher get this information? I got from data sheet. Data sheet is manufacturer's mindset. That's why I taught you before teaching you other stuff. But you have been rejecting. We don't need it. We don't need it. We don't. Okay. We don't ask you that. Do you need or you don't need? We give you a dose. Okay. So 3A. This is what? 4A. This is what? 4B. This is what? 4Y. So I didn't decide to... Where? Jessica. And Massa. Who was transmitter and who was receiver? Or each of you was transceiver? Transceiver? Then I come for this case. Also, here we have 4 and the gates. My dear student, this is fundamental of digital communication or digital electronics and digital communication electronics. So this is the fundamental for digital electronics and fundamental for digital electronics communication. Then again here we have another, so these are the input of another and the gate. At this point, we have input for another and the gate. Keep quiet. Then, for this case, we have also another, the force and the gate. So how many AND gates do you have? 4. Johanna now is writing. Joshua, take Johanna's pen and give him a clap. Okay, so let us come back. So this is first AND gate. Say first AND gate. Second AND gate. Third AND gate. Fourth AND gate. You cannot see them by your naked eyes. They have been built in within what? The integrated circuit. And this logic gates is just the bipolar junction transistor have been used as a switch. So one gate you might find that consists of more than one bipolar junction transistor, but it has been biased to operate as a switch. So without DC power, there is no biasing. Don't expect the output. Simple like that. So if you do not understand the bipolar junction transistor, then you could not understand what is inside logic gate IC. Simple like that. Because here we have a number of electronics, discrete components. We have electrical components, or electronics components, and semiconductor devices. So these are just the symbols. Okay? So we have input A and input B connected to the AND gate. It's not compulsory that you have to use the first gate. You may use the first one, or the second one, or the third, or the fourth. And in case you have been given an integrated circuit, you have to test all of them. Because students are using those integrated circuits, and maybe they have burnt out the first AND gate or the first exclusive OR gate. You have to check the second, you have to check the third, you have to check the fourth. So you could not say that, you could say that, my circuit is not working. No, maybe that AND gate is then used by others are fine. That's why you should understand the theory first before the practical. So we just take a jumper, we can use a copper wire, then we take this input. We take this input, and then first of all, we have to connect it to power. Remember that. We have to connect it to OT. So this one should be connected to the ground, common ground. And also we say that because remember you'll have a T block for the ground. You must have a T block for the hardware implementation where you'll have all the power rail in case of the breadboard, but in case of the Vero boards and PCB board, you need the T block for the OT, for the ground, and for the common power. Then, what do you say? So here we have this we call T, common ground power bank. So all of these grounds should be connected or should be drawn from here. So I mean that, for instance, that you can take a jumper and connect with this one. So we have connected the common ground. We have connected the power supply for the AND gate. So when you connect the power between pin number 14 and pin number 7, all the logic gates built in integrated circuits have power. Okay? So these are the common pins for four logic gates, or 6 logic gates, or 3 logic gates, or even 1 logic gate. You should not claim that all the ICs have 4 gates. No, you should not claim. It's your responsibility to go and check the physical appearance of the other integrated circuit. So then, so let us say that, or let us make decision. We say, okay, let us use the CD and the gate. And then we need again another input T, called T, put B. Okay? Okay? Limb is drawn. Why? You know the reason. What the color of LED that we'll be using there? A red. These concepts are very important when we'll be designing RF transmitter and RF receiver, after I taught you the concepts of encoder and decoder. Okay? So what the resistance of this resistor, massa? What the resistance of this resistor, massa? Massa is not in the class. Physically she's there, but 240. So resistance of this resistor, it's 240 ohm. Say ohm. Because you may just remember 240, but you forgot ohm. And 240 is meaningless. Class, are we together? Are we together? Eh? Remember that. Remember that. This ground is just a wire from here. This ground is just a wire from here. This ground is just a wire from here. As this ground is just a wire from there. Remember we said that in any electronic circuits, we need to have common ground. So simply, just see for the matter of representation, this is a common ground. So physically, you need jumpers. Are we together, class? Yes. Is it clear? Don't forget to label or to name. This is figure what? A? Figure 3. Then, what its name? So once you have that schematic circuit diagram, what you just need, just electronics components and build it and test it. Okay, my dear students, this is the end of workshop 3. I would like to thank you. I believe that you have understood. You have been enjoying it. And I would like to ask you to join me in the next workshop 4. So in workshop 4, we are going to discuss about workshop 4. Actually, I'll give you a task about something. I will not mention. But workshop 5, yeah, we'll have to discuss about encoder. And workshop 6, you have discussed about decoder. And then workshop 7, we have discussed about RF transmitter, especially 433 megahertz RF transmitter, and the 433 megahertz RF receiver. So I would like to invite you, join us to enjoy the beauty of digital electronics communication engineering. So welcome, but let me know. Class, did you understand? Did you understand what you've been learning today? Stop writing, stop drawing. It's time to congratulate you because you're doing a great job. I say stop right. 1, 2, 3. Ongera. Imara. Wow. Thank you very much. May God bless you. See you in the next workshop. Bye-bye.